In this video, we're going to be looking at heating curves and cooling curves, and we are going to be starting off with a heating curve. A heating curve is a graph of the temperature of a substance as it is being heated up over a period of time. So it's pretty straightforward, but it contains a lot of really valuable information. As we build, we're going to draw a heating curve here, and as we build our heating curve, let's imagine that we have an ice cube. So we're going to be starting off with a piece of solid water, water in the solid phase, and as you know from your experience with ice, it is going to be at a very low temperature. So we're going to start our ice cube down here at an extremely low temperature. Maybe we want to put some numbers on this axis, so let's just say that we're starting our ice cube at negative 20 degrees. This is going to be in units of Celsius. And so what we're going to do with our little ice cube is we're just going to start consistently adding some heat. We're going to add the heat consistently, so we will not change how much heat is being added. We won't, for example, start blowtorching it for a little while. We're just going to consistently add heat, and as you know from your experience, the temperature of that ice cube is going to begin to warm up. The ice cube is going to get warmer and warmer until it reaches a temperature where it begins to melt. For ice or water, that temperature is 0 degrees Celsius, right there. And when we hit that point where the ice begins to melt, what we actually see, and this is so cool, we see that the temperature of that ice as it is melting, it stays constant. So during this period of time right here, even though we're still heating it up, we're still adding heat to the sample, the temperature is not changing. It's just staying flat, like plateaued, which is really cool. This temperature we refer to as the melting point. The melting point, the temperature at which a substance melts. And that melting point is associated with this period where we have this plateau. So what's going on here at this point? Like why, even though we're adding heat, why is the temperature not increasing? During this period of time, all that the molecules are doing is they are converting from solid to liquid, and that takes a lot of energy. They have to break some of their intermolecular forces to do that, and they also have to start moving at a faster rate. So during this time, all of the heat that we are adding to our sample is just being used to break those intermolecular forces and speed up the water molecules. And none of that heat is being shown as an increase in temperature because the molecules themselves are absorbing all of that heat. Once that's over, once all of the water has been converted to liquid, then the temperature will start to rise again. So here we have liquid, and it's just getting warmer and warmer and warmer and warmer, until again it reaches another point where it starts to undergo a phase change. This is the temperature at which the substance boils. And for water, we know that temperature to be 100 degrees Celsius. And again, we would refer to that, the temperature where this plateau is taking place, we refer to that as the boiling point, the temperature at which the substance boils or converts from liquid to gas. And again, during this time, we have another plateau. Even though we are still adding heat, the temperature is not increasing because all of the heat that we are adding is being used to break intermolecular forces and speed up the molecules so that they can move from the liquid phase to the gas phase. This is something that confuses a lot of people, and they think that can't possibly be true, but you can test this for yourself. You can take some water, put it on your stove, heat it up, and start to boil it, and just put a thermometer in there and look at the temperature of your water as it is boiling. You'll see that it isn't getting hotter. It is staying at the same temperature. Once all of the water has been boiled and it is now converted into what we would call steam, water in the gas phase, then the temperature can start increasing again, and theoretically it just increases forever. And this is one of the reasons why if you've ever been burned by steam, that can be a really bad burn because that temperature, the temperature of steam is kind of unlimited. It could be almost, as high as it possibly could be. So a steam burn sometimes is really, really bad. It's definitely a higher temperature than boiling water. Let's label a few things on this heating curve. We've already labeled the boiling point, which is the temperature associated with this plateau, and we've already labeled the melting point, the temperature associated with this plateau. Let's also label these different features of the graphs right here. So at this point in time, we said this is where the substance is a solid. This is where we had ice, and the temperature of the solid is increasing. And then our second slope right here. This is where it was a liquid. And our last slope up, this is where the sample was a gas. And during the plateaus, this point right here, this is where the substance was melting. So this is where it is converting from a solid to a liquid. So here at this point, we have both, some in the solid state and some of it in the liquid state. If you imagine holding an ice cube in your hand while it's melting, during the active melting process, some of it is a solid and some of it is a liquid. And it's not considered done melting until all of the solid is gone and all that you have left is liquid. And then up here at this plateau, this is where we are boiling. And so at this point, this is where we have both liquid state as well as gas state coexisting. One last thing that I want to talk about while we're looking at this graph, we can get some information, we can make some generalization about the enthalpy of vaporization and the enthalpy of fusion for this particular substance. Let's just kind of make a note up here in the corner, the enthalpy of vaporization and also the enthalpy of fusion. This is the amount of heat that is necessary to make these phase changes take place. So the enthalpy of fusion is the amount of energy or heat that it takes to melt a substance. And the enthalpy of vaporization is the amount of energy or heat that it takes to boil a substance. When a substance has a very low enthalpy of fusion or a very low enthalpy of vaporization, that means it doesn't take very much energy to melt. It doesn't take very much energy to boil. When a substance has a low enthalpy of fusion, we see the period of time where it's in this plateau is very short. So low enthalpy of fusion is going to have a short plateau, just short meaning in reference to time, that this process is going to happen pretty quickly because it doesn't require very much energy. If a substance has a very high enthalpy of fusion, meaning that it takes a lot of heat to make that change take place, we'll see a long plateau for fusion or a long plateau for vaporization. So let's make a note of that up here. If we have a low enthalpy of either vaporization or fusion, that corresponds to a fast plateau, fast in terms of time. And so that means that these plateaus will be very short. So if you're looking at two substances, if you're comparing them side by side, you can look at the length of this plateau and make some generalizations about the relative delta H vaporization and fusion for those two substances. The second thing that we can get from a heating curve or a cooling curve is a little bit of information about the heat capacities. The heat capacity C, which is a measure of, let me write this down up here, heat capacity C, which is a measure of how much heat it takes or how much energy it takes to raise the temperature of a substance. So if a substance has a very low heat capacity, a low heat capacity means that it doesn't take very much energy to get that temperature to go up really high really fast. If a substance has a low heat capacity, we're going to see that reflected in the slopes of the heating curve and the cooling curve. Low heat capacity, again, that means the temperature goes up fast. So a low heat capacity substance is going to have a very steep slope. The temperature is going to go up very, very fast. And if something has if something has a high heat capacity, that means it takes a lot of energy to raise the temperature. So a high heat capacity is going to have a pretty flattened out slope. And we can see that reflected at any one of these points on the graph. So the slope, the intensity of the slope is a measure of the heat capacity of the substance. So here we can say if we have a low heat capacity, that corresponds to a very steep or a sharp slope at any point on the heating curve. Let's very quickly look at a cooling curve. It's basically the same thing, but in reverse. So in a cooling curve, this will be a cooling curve. We are starting at a high temperature, and then in this situation, we are removing heat, of course. We're cooling it down. And so all that we see here is just the graph in reverse. All of the same features. We are starting off in the gas phase, and we are lowering the temperature until we get to this point, which is where we have both gas and liquid coexisting simultaneously as the substance condenses, turns from a gas to a liquid. Then we have our substance in the liquid phase as the temperature is decreasing until we get to our second plateau, this temperature over here. And at this plateau, this is where we have both liquid and solid, because this is where we're freezing. And then once everything gets frozen, we have solid down here. The temperature drops. Theoretically, the temperature drops to infinity. This first plateau and this plateau as well, we still refer to these as the melting point and the boiling point. Even though in this particular graph, we aren't boiling, we're actually condensing, and we're not melting, we're actually freezing. But we still refer to the temperature as the boiling point and the melting point. That's just standard in science. The temperature itself is the same, whether you're moving from the liquid state to the solid state or from the solid state to the liquid state, that the value of that particular point on the heating curve, the value of the temperature is the same regardless.